Okay, so I would like to greet everyone. My name is Anna Georgina Kopasz. I'm a first-year PhD student at the Biological Research Center of Szeged. And today I would like to talk about my work from the past 5 years that I spent in the Laboratory of Cancer Genome Research under the supervision of Dr. Lajos Mátés. So, genetic manipulations to modify gene expression in a cell or in an organism have been applied in numerous fields, including basic and applied research, industrial biotechnology, medical sciences, agriculture, and so on. The purpose of gene expression modifications can be to investigate or discover the function of mammalian genes through the generation of gain of function and loss of function phenotypes. So, genetic alterations often cause several types of diseases, for instance, cancer, which is the leading cause of death worldwide. Nowadays, the current high priority of cancer research is the identification of so-called cancer driver mutations facilitating disease progression among the more abundant passenger mutations found in tumors. The cancer genome landscape consists of so-called mountains, so genes frequently mutated in many different types of cancer, and hills, which are genes which are less mutated in less type of cancer. So only with bioinformatic methods, these hill-type mutations cannot be distinguished from passenger mutations. So there is a growing demand for in vivo test systems for the validation of potential cancer driver alterations with low penetrance. So because of this, our main aim was to create one mouse model in which we can investigate all potential cancer driver alterations of hepatocellular carcinoma in a single experimental model. So how have this model been established? First, the basis of our animal model is a fumaryl acetoacetate hydrolase deficient mouse strain, so Fa deficient mouse strain, which is the animal model of tyrosinemia type 1. Without fumaryl acetoacetate hydrolase enzyme, animals die neonatally due to the accumulation of harmful metabolites like succinylacetone in the liver. However, animals can be rescued with a drug called anti-BC, which inhibits the tyrosine degradation pathway and converts tyrosinemia type 1 to tyrosinemia type 3, a milder form of this disease. Upon gene therapeutic treatment of Fa cow mice, we inject a plasmid mixture into the tail veins of Fa cow mice hydrodynamically. So this plasmid mixture contain a transposon plasmid coding the Fa therapeutic gene, or from another aspect, the Fa selectable marker gene connected to the transgene of interest, and a transposase coding helper plasmid. After hydrodynamic injection, a huge amount of plasmid mixture can reach the liver, and those hepatocytes which are able to take up both plasmids and in which the transposase can express and can build the transposon into the genome will survive, and they will start intensive liver regeneration. In this way, we are able to rebuild the whole liver by replacing hepatocytes to transgenic hepatocytes and creating a whole transgenic organ within 3 months. So, in this system, nearly 100 million testable hepatocytes are available in a single experimental animal to validate potential cancer driver alterations with low penetrance. So, to validate these mutations, we had to connect the potential oncogene, the Fa selectable marker gene, the M-cherry fluorescent marker gene, and the microRNA against the tumor suppressor gene into a single transcriptional unit. Besides, we also had to optimize artificial microRNA-based gene silencing. So we built up our technology step by step by using fluorescent marker genes to follow transgene expression and RNA interference-based gene silencing efficiency. However, it is well known that RNA interference-based gene silencing often shows toxicity and viability issues in transgenic mice due to the high expression level of shRNAs or microRNAs. To overcome this difficulty, we plan to use an endogenous bidirectional promoter, which provides milder expression level of microRNAs. By using this promoter, we were able to express transgenes at a well-balanced and physiological level, and we were also able to create an efficient GFP knockdown by using an artificial microRNA element against GFP without any signs of in vivo toxicity. So next, to better explore the impact of multinodular regeneration on the long-term transgene expression, I built the luciferase coding sequence into our newly created transposon vector, and then we injected this transposon plasmid in the presence of transposase coding helper plasmid into the tail veins of both wild-type and FAKO mice. Then we monitored the transgene expression level for 3 months by detecting bioluminescence in living animals with IVIS Luminous 3 in vivo imaging system. In comparison to the standard hydrodynamic injection method in wild-type animals, the transgene expression level of FAKO animals after 3 months was stabilized more than 5,000-fold above the level detected in wild-type animals, which also proves the robustness of our technique. So, to show the utility of our technology in silencing tumor suppressor genes, we created transgenic livers processing either 1 or 2 different p53 microRNAs. Then I performed RT-qPCR measurements on these livers, and my RT-qPCR data showed that the GFP and the mCherry-T2A transcript levels weren't significantly altered compared to the control. This is in line with my transposon copy number measurements, since neither of them reveals serious toxicity issues associated with microRNA expression. Regarding the p53 knockdown efficiency, we were able to create a robust p53 knockdown in the case of both 1 and 2 p53 microRNAs. So next, to show the usefulness of our technology in cancer research, we used the well-known driver combination, and we silenced p53 tumor suppressor, and we overexpressed HRAS G12V, which is a constitutively active and oncogenic form of HRAS protein. So, experimental animals couldn't be housed for longer than 5 weeks due to the high number of HRAS-transformed hepatocyte colonies in their livers. So, we sacrificed the animals after 5 weeks, and then I performed RT-qPCR measurements on the transgenic livers. My RT-qPCR data show robust p53 knockdown in the driver-treated livers, and interestingly, we can also see a huge, almost 7.7-fold decrease in the extent of transcript B, so the extent of transcript HRAS G12V compared to the control GFP transcript. This is probably due to the adverse effect of the mutant HRAS protein. So, to show the appearance of tumor characteristics, we injected 1% driver construct mixed with 99% therapeutic construct into the tail veins of FAKO mice. 5 months following the injection, huge tumor burden was observed, and on histological images, we can see frequent neoplastic invasions, atypical mitosis, and high intrinsic fat accumulation, which are typical for hepatocellular carcinoma. So then, for further characterization of the induced tumorigenic processes, we analyzed all the livers by using immunohistochemical stainings for AFP, so alpha-fetoprotein, and GPC3, so glypican-3, one of its early markers of hepatocellular carcinoma. After 5 weeks, as we expected, we can see positivity for GPC3 almost all hepatocyte colonies, while we cannot see almost any positivity for AFP. 5 months following the injection, mature tumors were positive strongly for both hepatocellular carcinoma markers. So, in conclusion, we built up a test system to validate potential cancer driver alterations. And the biggest advantages of this technology is the tag-free expression of any oncogene and silencing any tumor suppressor gene in the mouse by using an endogenous bidirectional promoter. This is a high-throughput method with 100 million testable hepatocytes in the mouse liver, and this model is also suitable for modeling the sporadic nature of cancer. And finally, we published this test system as a methodology article this April into the BMC Biology Journal. And finally, I would like to thank for my supervisor, Dr. Lajos Mátés, and all of my former colleagues and collaborators, and thank you for the attention.
Thank you for your presentation and stay on the stage, and I would like to ask Professor Mátés to join to us, and we will give the diplomas for the award.